In this video, I will be showing examples including limits and continuity, and using concepts that we have learned from previous videos. To continue on with this video, we need to remind ourselves of the left side limit and the right side limit. Here, the left side limit is approaching A, while the right side limit here at C is approaching B. And we can see that the left side limit is coming from the left side and the right side limit is coming from the right side. The first part of the question says, suppose that f of x is equal to 2 for all x smaller than 3, and f of x is equal to negative 4 for x is larger than 3. Without even looking at the first part of the question, we can draw a graph from this statement. As you can see here on this graph, when x is smaller than 3, the y value is always 2. And when x is larger than 3, the y value is always negative 4. I put 2 holes here because, as it says here, x is not equal to 3. This is only when x is smaller than 3. And same here, this is only when x is larger than 3 and not equal to 3. The first part of the question asks, what is f of 3 if f is left continuous at x is equal to 3? We can see that from the left, f of 3 is equal to 2. The second part of the question asks, what is f of 3 if f is right continuous at x is equal to 3? We can see that from the right side, as x approaches 3, y is negative 4. The next example asks us to determine the points of discontinuity of the function h of z is equal to 1 minus 2z over z squared minus z minus 6. To find points of discontinuity, we can factor the denominator into z minus 3 and z plus 2. Then we get h of z is equal to 1 minus 2z over z minus 3 times z plus 2. Because the denominator cannot equal 0, there would be no graph when the denominator equaled to 0. So then we can do z minus 3 is equal to 0, in which case a graph does not exist where z is equal to 3, and we can do z plus 2 is equal to 0, and z is equal to negative 2, and a graph cannot exist there either. These would be our 2 points of discontinuity. When we graph the function, we can see that no point exists at negative 2 or 3. Even as we zoom out, there is an asymptote at negative 2 and 3. Our next question asks us to sketch the graph of f of x, and at each point of discontinuity, state whether f is left or right continuous. They've given us that f of x is equal to x cubed plus 1 for when x is larger than negative infinity, but smaller than or equal to 0. F of x is equal to negative x plus 1 for when x is larger than 0 but smaller than 2. And f of x is equal to negative x squared plus 10x minus 15 for when x is larger than or equal to 2. Our first step is to graph x to the power of 3 plus 1 when x is smaller than negative infinity and smaller than or equal to 0, which I've done here. This line goes all the way till x reaches negative infinity and stops at 0. Our second step is to graph f of x is equal to negative x plus 1 when x is larger than 0 but smaller than 2. This blue line is that function, and I put a hole here when x is equal to 2 because x is not equal to 2. Our last step is to graph f of x is equal to negative x squared plus 10x minus 15 for x is larger than and equal to 2. So that's this green line over here. I put a closed dot over here because x at this point is also equal to 2. And here, this keeps going all the way until infinity. This video summarizes how to recognize left and right continuous, how to determine points of discontinuity, and how to draw a graph. Sorry, my bad. The last part of this last example asks to state whether f is left or right continuous at each point of discontinuity. Here we can see that this point is right continuous, and this point here is left continuous. As I was saying, this video has summarized how to recognize left and right continuous on graphs, to determine the points of discontinuity, and to sketch the graph when given certain restrictions. And that's it.